And you can kind of modify how much you write, because you'll see some of this stuff that's kind of familiar to your web quest and your reading guide, which I will pass back soon. So if something goes to completion, how do you know it? You can look at the DCE. What do you notice about the arrow here? It goes forward. There's no choice or option for it to go in the reverse direction. To completion means goes forward, and that's it. At the end of a completion reaction, which is pretty much every reaction that we've talked about so far, because I didn't want to scare you too soon, everything we've done so far, at the end we have essentially 0% reactants left, and we have 100% products made. That's kind of how we phrase it. We have 0 reactants left, 100% products made. Now I know there's those special cases of limiting reagents, those ones you guys love, and there's excess reagent left over. I know, you missed the good old days of stoichiometry. But sometimes there are some things left over, but we're going to kind of ignore that special occasion. So that's what a completion reaction is. What are some evidences of chemical reaction that help us to see a reaction has occurred?
Bubbles.
Bubbles, so let's go gas evolution. What else? Okay, so color change, that's unexpected. Keep going. Heat evolve. What else? Thank you. Precipitate, it's the bottom of the test tube. What else? That's pretty good. I'm feeling it. We're good here. So we know that there are things that form that help us to see that a reaction has occurred to completion. There is one substance that formed in a neutralization reaction that's also going to help us see a reaction has occurred. What's a neutralization reaction? Yields salt plus water. Water is a pure liquid. So these are things we just said. Forms a gas, forms a pure solid precipitate. Pure water is something else. So if I ever say pure liquid, I'm talking like water liquid, not aqueous solutions. And that's a very specific way to write it. You make sure you put your L afterwards. And we're going to talk about why this is significant in just a moment. Next one. Told you that some of this is review. Okay, so this is anything that we talked about pretty much thus far. Now we're going to talk about how we can go back and forth. We can have equilibrium reactions. What's the first thing you notice that's different about this VC? Oh my gosh, it can go backwards. So we have a reversible reaction, okay? It equilibrates forward and reverse at the same time. So a reaction as making a product can go back and reform a reactant. Equilibrium is a kind of special time though. There's a couple of things that are characteristic of it being at equilibrium, and I'll let you write down some stuff and then I'll talk some more. When rate of forward reaction equals the rate of reverse. I don't know why it's cut off here. And that's just like purely the definition. So we have, at the end at equilibrium, we will always have reactants remaining and products remaining. Oh, I forgot to define dynamic. You guys can define that. What's dynamic mean?
Constantly changing.
Constantly changing, right. So constantly changing, meaning that we will always have products going in the reverse direction and always have reactants going in the forward direction. There's no stagnant time. They're constantly going back and forth. So they never stop changing. But though they never stop going back and forth, they come to the point where there's no net change. What do I mean by net change? Total overall change. So if I give Jack $1, he gives me $1 back, what's the overall change? 0. Nothing actually changed, but we were still exchanging monies. So the reactants are left and products are left. There's no net change in. What does bracket mean here? Concentration molarity, right? So the concentrations are not changing overall. And there's a misconception about what does that actually mean. I'm going to draw a picture to help represent that. this was what we drew yesterday, or we saw an example yesterday on the notes for rates. For rates, we had concentration on the y-axis and time on the that one, x-axis, I want to say z. At the very beginning of the reaction, you have reactants. Over time, they decline. Yeah? Over time, products are made. They go up. At the time when the rates, the slopes right here and here, once they stop changing, what is happening to their concentrations? So their concentration of the products formed are equal, are constant. The concentrations of the reactants left are constant. That definition is right here. No change in either product or reactant concentration. So you can see equilibrium graphically when the slopes of these lines are now horizontal. Are the concentrations of products and reactants equal at this point? No. That is a big misconception. You're like, equilibrium, everything's equal. No, not true. I mean, they can be. They can end up at the same exact line and kind of converge together, but that's not true in this case. So that's why this right here is a big misconception. Another way to represent the products or reactants in which one you have more of at equilibrium is through I'll show you this in a second actually. Look at the graph I've written out here. Which is greater at equilibrium, products or reactant concentration? Products, because we have the products starting off at 0 down here, and then products going up here. See how products are higher? Reactants, which you started off with, there's reactants down here, they're lower. Okay, so products are higher at concentration. There's a way to represent that with these arrows. Which of these arrows do you think represents that there are more products in equilibrium?
The water.
The one on the left, good. This one left. Is that one? Thank you. Bye. Okay, so this one right here is showing more products are formed. This one right here is showing more reactants are formed. Can I go forward? Okay, some of us are like, yes, please. Some of us are still writing. So, from your reading guide, you might remember this. What letter is our equilibrium constant? K. K, we're just going to go K. Keep throwing stuff. Because K can be representing any type of reaction. Ka, Kb, Kq, Kp, Kc. There are all these different little subscripts that go with it to represent the type of reaction. So I'm just going to write K. And that's our equilibrium constant. That's a value. When the products were favored, was K greater than 1 or less than 1? You wrote this out in your reading guide. Take a guess at it. Greater than 1. This one, K, is less than 1. We're going to talk about mathematically why that actually makes sense. So some of you are very math-minded, so you need the math behind it. And going forward now. Okay. So, the equilibrium constant, which I kind of just spoiled that news. There it is. It's K. It has a meaning to it. It is telling you about the extent of the forward direction. What are you making in the forward direction? Products or reactants? Products. You're making products. So it's telling you how many products are formed relative to the amount of reactants left or formed. So give yourself a second to read or write any of that, and then we'll talk a bit more. I'm going to throw some papers at you. The words, stuff like this is something you'll probably see on multiple choices more conceptual. So the extent of the forward direction is experimentally determined by this constant K. It is also a constant at a specific temperature, and so that specific temperature might be given in the problem. Ignore it. It is like people, when they give you a drink, they're going to say, they're probably not going to ask if you want ice, okay? You just get ice. It's customary. It comes with a problem. You get the temperature. and it doesn't affect anything. So you'll always have a specific temperature denoted. The larger the K value means that you're going to have more products. That's why K greater than 1 is representing that products are favored or there's more of them at equilibrium. So I want you to draw yourself 2 little graphs along with this example. Label them concentration versus time. Concentration versus time. I want you to draw one of them where K is greater than 1, products are favored. And then the other one, K less than 1. What does K less than 1 mean? Reactants are favored. So tell me how you're drawing the products favored one. Okay, but you're always representing both reactants and products on the same graph, right? So you're starting off high with reactants, and you're going down, low, really low, okay? For products, you're starting off where? Low, and are you crossing the green line? Or are you going to stay below the green line? Why are you crossing it?
I have more products.
Correct. So at equilibrium, the products are a higher concentration. How is that going to look different for the K less than 1?
It's gonna stay below 1.
But still increase and decrease, right? So are they going to cross? No, they're not going to cross. So our reactants here are going to still start in the same place, but go low-ish, not real low. And products are going to start at 0 and go up, but they're not going to cross the green line because the reactants are still of greater quantity than the products are. Cool? So the graphs are really, I mean, they mean a lot. They can tell you a lot about the reaction. So the reactants are higher here. I'll give you guys a second to absorb that. I'm liking all the colorful pins and helping people out here. This is good. Kind of go forward almost here. Some of you guys are like, yeah, sleepy. Why are you so sleepy? Gosh, it's not Monday, it's Tuesday. It's Tuesday. Okay, let's talk about what the constant means now. So the constant is a number. It is a constant. It's a value. It can be represented in an expression as well. The expression is just a bunch of variables together. Then we're going to show that expression is related to a reaction and so forth. So we're building here, okay? Here is a BCE, a theoretical BCE. What are the little A, B, C, and D representing? Say again? Molar ratios. Let's go back to like less smart individuals. Let's go coefficients. Less sophisticated answer. Yeah? They're just coefficients. All right, so coefficients in front of these are going to be very important. The equilibrium constant is K. It is related to a specific reaction, so a specific BCE. It also has this like theoretical law behind it, the law of mass action. Nobody knows what the law of mass action is, just know that it's related to the equilibrium constant. It's like, it's just a law we have to know. It's like, who came up with the word gravity? Who came up with the word law of mass action? I don't know. What does gravity really mean? What does butterfly really mean? Why do they call it? Well, why does gravity mean gravity? And he was just like kind of sputtering out some words.
Was my red different to your red?
It's just the name.
The same red. And he's like, what is it? Click. That's not.
Just making up words. Just making up words. We'll have a philosophy debate later.
There's no way to prove
We'll talk why words exist later. So let's talk about the K first. The BCE is relevant here. The definition of the equilibrium constant is as simple as it can get, is just concentration of products over concentration of reactants. So what we have to do is we have to represent the product of the products over the product of the reactants. And when I say product, I mean mathematical product. You're multiplying together, right? So what are the products over here on this reaction? Who are the products? C and D. Okay, you take C concentration to the little c power. So you have to use the coefficient as an exponent. d to the d power, because that's its coefficient. Okay, so there's our products. Who are the reactants?
You multiply them?
Yes, you're multiplying them together. You're not adding them together, you're multiplying them together. Who are the reactants? A and B. So A to the A power and B to the B power. So whatever the reactants are, you look at their coefficients and you turn them into exponents here. So this is how it's always written. And there are a couple of exceptions though. If our reactants or products are pure solids or pure liquids, their concentration is irrelevant because their concentrations do not change over the span of a reaction. Because the concentration is moles over liters, right? Moles of solute over liters of solution. But if you're pure, do you really have a solvent or a solute? No, you are one thing. You're not a mixture. That's why the concentrations of pure solids, write this down, pure solids and pure liquids are irrelevant. So mathematically, this does make sense. You told me K greater than 1 meant who was favored, products or reactants? Products. So for the K value, which is greater, the numerator or the denominator? To make K greater than 1, which is greater, numerator or denominator? Numerator. So you have more products over less reactants. That's why that makes sense. How in the heck does K get greater than 1? You had a bigger numerator. What does a bigger numerator mean? More products. That's why K greater than 1 means products are favored. And then, same story. K less than 1. How does this ratio look? Less products, more reactants. And that's why we say reactants are favored, because there's more of them. K is less than 1. Thumbs up if that makes sense. Yay, math. Cool, okay. We'll go further in just a second. This bottom stuff, we've already talked about. I'm not going to have you write it down. Molar ratio, molar concentration ratio, top and bottom. Which side of the reaction is favored? We just talked about that too. So let's do some examples. Yeah. Okay. Tell me what the K expression is for the first one. K is equal to. Give me names to use your knowledge. Concentration of not NO. Nitrogen. Monoxide. Okay. Concentration of nitrogen monoxide squared over nitrogen gas times O2 gas. Good. It's really easy. Take your products, put them up, put your exponent as a, or your coefficient as an exponent. Take your reactants, multiply them. Go ahead and do the second one too on your paper. So you don't have to rewrite the B's to E's if you want to. Tell me what you're writing for the next one.
Ammonium chloride.
No, just ammonium. And then
Oh, that's a solid.
It's a pure solid. Right, look, right there, pure solid. So don't write it. You can't write it. So you can put a numerator 1. Okay? So because the products are not related or they're not important to the equilibrium constant, so the products here are not written. You just put a 1 in their place. All right, now continue.
ammonia.
So on the denominator, ammonia and hydrochloric acid. Concentrations. Cleo. Because why is it 1, guys? Pure solids, and pure solids are not included in our equilibrium constants. It would be the same if I had written that, and maybe I've written HCl as pure liquid, you would not include that one either. So it'd be a pure S or a pure L, and that would say don't write. Okay, you guys do. Yeah, question?
How would you solve it though?
We're going to get to examples. Right now it's all theoretical. We have no numbers. We'll get to numbers. Okay, you guys do those. It should take you no more than 3 minutes. Do the K expressions, the equilibrium expressions for those. You don't have to write the BCEs again. I'll scroll down and see. All right, I'll scroll down so you guys can see the bottom ones. I'll scroll back down in a minute. You guys tell me what you got for the first couple first. All right, so shout it out. K is equal to, uh-huh, uh-huh, water, gaseous water, squared. Okay, that one was okay to write because it's gaseous water vapor. It's not a pure liquid. Okay, so that was fully included. And so if I gave you values to put in here, you could plug them in and solve for the K value. Next one, tell me what you got here. K is equal to carbon monoxide's concentration times hydrogen gas concentration over.
1.
Okay, 1 goes there for the C, but I'm actually not going to write it because it's just 1 times concentration of H2O to the first. Okay, you can put a 1 there just to remind yourself that it's a pure solid, and you put a 1 there to ignore it, but it's irrelevant for the mathematics of it, so it's okay to exclude. Next one. Yeah. Next one. Loud and proud. All right, B and I. Tell me the name of this. Thank you. Concentration of carbonic acid over concentration of carbon dioxide. That's it. Pure liquid water, right? Ignore. Yeah. Good? All right, so far all of these have just been general equilibrium. So these might have to little subscripts of maybe KEQ, just to say general equilibrium, or KC to represent K of concentrations, equilibrium with concentrations given. So these are 2 designations of 2 different types of equilibrium, but they're really just products of reactants, right? So I'm going to show you some of these as we go because they'll be coming up here in some examples. Keep going. Next one. K is equal to concentration of magnesium ion, bromide ion, squared. Sorry, it's really hard to see, but there's a squared up there. Over 1. Okay, I'm actually not going to write the over 1. because you're going to start to see that you can just exclude the ones, because except in a numerator, because it looks kind of dumb if you don't have a numerator on something. But that's just over 1. So there is an example of a solubility product 1. You know from your reading guides, KSP, solubility product? It's of something that is starting off as a solid precipitate, and then as it dissolves in solution, it makes ions. These ions are called, it's called the solubility product because it's the product of 2 ions that are soluble. So this one's labeled KSP. Write down these designations, so I'm not going to go over what they mean again probably. But KC and KQ are just general equilibrium examples. KSP is a very special equilibrium where you have a precipitate yielding 2 ions. Okay, keep going. What is this one? K is just 1. Good. What does 1 mean? It's 1 over 1, right? So what does this like actually mean when it's 1 over 1? Concentration of products are equal to concentration of reactants. That's the only time we're allowed to say that because it's actually 1. So that's a special one. 6, and I'm going to scroll down for this so you guys can see a bit better. K is equal to hydronium. Acetic acid. Anything else? Okay, pure water. Pure water is out. Don't write it down. What do you notice about this reaction? Maybe tell me what it's acting as. What is this one acting as? That's the, what kind of acid? That acid. What kind of acid? Ronson acid, thank you. Ronson-Lowry acid. Ronson-Lowry acid donates its H plus over to water to make hydronium, right? It's also acting as an Arrhenius acid because it's in water making H3O pluses, okay? So we can kind of refer back to a lot of reaction types. You'll notice some summation of everything here. If I told you the K constant, and I said, I also told you acetate and acetic acid, I told you the K constant, I could ask you to solve for that, right? If you solve for that, what could you find from that? The pH, foreshadowing what to come, okay? So you're going to start to combine acid-base chemistry with equilibrium. Okie dokie? Is that a strong acid or weak acid? Weak acid, okay, just reviewing. All right, this right here is what we're going to do. There's on your paper. Find it. We're going to do 1, 2, and 3 right now. I think I'm going in a different order. I'm doing number 2 first, okay? I'm doing number 2 first. Looks like this. Okay, so for this first reaction, gaseous equilibrium, there is our reaction. Yeah. That's not all of that. Okay. Here's our reaction, and I'm telling you it's gaseous, so everything's a gas here. The equilibrium concentrations of A, B, and C are blah, blah, and blah, respectively. What is the value for the K? Step 1 you should always do, because you're going to mess yourself up if you don't, is write out the K expression. So let's do that. What is the K expression for this reaction? Concentration of C.
Over concentration of A.
Okay, so we were good to include all reactants and products because they're all gaseous. No pure solids, no pure liquids. I would write down these 3 examples with me, okay, people? So using this one and the concentrations given, we've done the first step, do your expression. Second step is just to plug in. Okay, just gonna plug and we're done. This one's really easy. Tell me, what are you plugging in?
1.02 times 10 to the power minus 2.
Okay, so 1.02 times 10 to the negative 2 molar. Okay, because it is a concentration. That is our C. What's wrong with this still? Squared. Make sure that you refer back to what your expression set up was. Over
2.25, 5.50 times 10 to the power minus 3 squared.
and
Times 2.25 times.
cool. So that's really helpful to set up your expression first, that way you don't forget where your squareds are going. Calculate this for me now. I want to make sure you can plug this in your calculator appropriately. Over, use your parentheses. Thomas, it'll make it easier. own calculator. It's doable. It's not pretty. Doable. Because you're going to have to do some of these tonight, and I don't want you to get wrong answers because you can't use your calculator appropriately. Shout her out when you get there.
0, 4, 8.
Recalculate. Recalculate. Look at your parentheses and stuff. Huh?
You got 8,207.2.
I got 1500.
Thank you, Lord. All right, say again. 1530.
1528.
I'm rounding. 1530. Oops. See how I told you? Might want to practice putting these in your calculator. So Clayton, tell me how you did it in your calculator.
I used the shortcut that gives you an automatic fraction 1 over 4.
Okay, you just need to do the numerator equals divided by parentheses, parentheses, blah, 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 parentheses, parentheses. That way your whole entire denominator is contained in the denominator. Recalculate until you get that, because I don't want you guys to miscalculate and have your work right. You know, you have some success with the calculator. Who got this? Thank
I
you.
got 50.
5 people out of 30.
Wait, is that an exact answer?
No, it's 528, 1528. What do you notice I did not put at the end here on my answer? No units. Good notes or good news. No units on your K value. Okay, they never have units. All right, you can recalculate that on your own time. We're gonna go and complete the rest of these. What's up? You need to put this over bracket, parentheses, squared, to negative third, bracket. You need to either calculate solely the numerator and then solely the denominator and then divide, or put lots and lots of parentheses to keep that exponent.
I tried doing this solely. And it
Still didn't get it?
got it wrong.
I'll look at it later. I'm moving on. We can practice calculating. Continue with number 2 with me. This is the methanol example. Methanol is manufactured according to the following equation. The equilibrium constant at 400 Kelvin for the reaction is 1.609. Which of those values is actually important in that second sentence?
1.
All right, this is the equilibrium constant. What do I mean by equilibrium constant? K. Okay, so this is K. I'm not always going to say K is equal to 16 or 1.609. I'm going to say the equilibrium constant at a temperature, right? This is the temperature thing I told you about. Ignore it. It's irrelevant. It's just going to be like standard there. That's our K value. The equilibrium concentrations are blah, blah, blah. What is the H2 concentration in the vessel? So now we're solving for one of the concentrations. So tell me the K expression first. What's the K expression for this reaction? The expression, not the value. Give me your K expression for this reaction. So methanol concentration over, anybody? Carbon monoxide and squared. Okay, cool. All right, so we know the values of 2 of these, and we're going to solve for the last one. So methanol was given as 0.818 molar. Carbon monoxide was given as 1.402 molar. And H2, we don't know, I'm going to call it X. Is this all good? Liars. What's wrong? And you make sure you square it. If you don't write your expression first, you are going to forget to square it, okay? Trying to make sure that you're good with that. So now this whole thing equals what? Tell me how you are mathematically going to solve that. Do not use the solver on your calculator.
I take the 1.402 the
And
other side, multiply it.
so multiply this on the side. So 0.818 over x squared is equal to that times that, which is like 2.2558. Okay.
I should take the x squared also, and then divide 2.
Okay. So we take the x squared over here as well. I'm good with that. All right.
Then take the 2.25.
So divide by 2.2558. I'm thinking that's right from memory. Forgive me if I'm slightly off there. So x squared is equal to what? Anybody? Thanks, Victor.
0.319.
Let me make sure that I did that.
Also, it's 0.3197.
I got 0.36 something.
Yeah,
What did you get? 362? Okay. I remember it being 0.36. Okay. Now we have x. That's our or we don't have x. We have the x squared, so we need to square root that. So it's like 0.609. What is it? 602? 0.602 molar is equal to x. And who was x? H2's concentration. So the final answer should be kind of written out like that, so I can see that you actually know what x was referring to as well. So I just worked through the math there. I'm not going to work through the math probably on many others because you're Algebra 2 qualified, and this is Algebra 1 for sure. Okay, so there's our concentration of hydrogen gas. Last one we're doing together right now, and I'll do an icebox after this. Tell me how you're going to, actually you guys got this, solve this one. Take a minute or two and solve that. If you have already, then while you're waiting on the rest of us, you can start number 1 on the problem set. Honey, where are we here? We're doing these 3 examples. Okay. I believe this is number 1 on yours, right?
Yeah.
Yeah, you're doing number 1 on yours. Who has the answer for me for K? Levi, what is it? 0.041. Give me one more. 3.0143. No units, okay? K has no units. Yay! So you just simply are putting products over reactants with their exponents, the coefficients as exponents. This one happened to be the same, so I just like squared that. You can see that's the same concentration. Does this mean reactants or products are favored? Reactants, because K is less than 1, so reactants are favored. So what would our graph look like? Reactants would slope down, but not cross the product line. Okay, we have 2 more questions we're going to do together. More complex, more involved. And this is your paper to keep as well. I'm passing out right now. I'll put that one. How is this so far?
Not that bad.
Not that bad? Hannah, what's up? One more. Okay. Oh, don't write that down. I'll come back to some of the notes. I want to finish up a couple practice problems. Oh, I can't tell you that. So that means okay. Find the one that is, so worksheet 1, chapter 18. It says chapter 1, 18. You got it? You guys can do 1 and 2 later because you're qualified to do that by yourself now. I'm going to do number 3 with you, okay? So here we go. You can write on this as yours. I don't think you have enough space to write all this stuff, so I would recommend you writing on a separate sheet of paper, but some of you guys write like ants, so you can do it if you want to. But working through number 3 here. So I'm going to actually rewrite my BCE because it's hard to see. As you're looking at the BCE, what's the first thing that you notice? There's a solid, right? 4D solid. So we already know that's going to be important. So the first thing we want to do is write out the equilibrium expression. So leave yourself some space, write your BCE out, leave some space underneath it. We're going to use that space. Write the K value down low. What is the K, I'm sorry, the K expression. What is the K expression? Concentration of C. Okay, so we're really good at writing out our expressions at this point. Baller. Now we are going to learn about something called an ice box. Ice boxes are representing a couple of the different parts of a reaction. So when you start reading this first part of B right here, the initial concentration of A was 4.0 molar and B was 4.0 molar. We haven't been talking about initial this whole time. We've been talking about equilibrium, right? So normally in a reaction, you put 2 things together, they react, and then they come to equilibrium. So when you first put 2 things together, that is called I. That is called initial. So below your BCE, write down ice. This is called an ice box. Okay? So at the beginning of the reaction, you have initial. During the reaction, there are changes happening. So what does C stand for? Change. And guess what E stands for? Equilibrium. Okay, that's kind of the topic of the day, right? So we need to get to equilibrium. This whole time I've been giving you equilibrium concentrations. That's why they were so easy. So now we're going to work a little bit backwards. The initial concentration, which is I, for A was 4 molar and B was 4 molar. So write 4 molar underneath I for both of those. Does it give you the products initially in this problem? No. So what are you assuming you have for products initially? Good job. Nothing. Good, guys. Great. Nothing. You have no products. I was hoping nobody would answer. Because there's nothing to start with. You only have reactants to start with. During the reaction, though, it says, blah, blah, blah. If at equilibrium, 2.0 molar of A has reacted. So how much of A has reacted? 2.0 molar. That amount reacted. So where's that going in our table? It's going into the chain part because that's what actually is happening during the part of the reaction. So if that much reacted, that means it's taken away. So you're subtracting 2.0 molar here. Does that make sense so far? It's being consumed. Well, during a reaction, the reactants are going to react. So what's going to happen to their concentrations? They're going to go down. So you're subtracting a specific amount from here and here. Well, what's going to happen to products over time? You're going to add products over time because it's the law of conservation of mass. If you take away reactants, you're adding products. But you don't just get to willy-nilly add whatever you want. You have to look at the ratio in which they react. This happens to react. For every 2 A's, you make 1 C. For every 2 A's, you make 4 D products, right? So you've got to deal with these coefficients as You subtract and add things. So really what's happening is 2 parts of the reaction reacted here. So this 2 here is actually equal to 2x. So I'm going to write 2x right above that because of the 2 coefficient. So I'm subtracting 2x. Well, what's x equal to if I already know 2x is equal to 2? X is equal to 1. So you figured that out at the very beginning and then you utilize that knowledge throughout. So you're subtracting 2 parts here. You're also subtracting 2 parts here. What are you adding here? 1 part. So you're adding 1x here. I'm writing these little because these are like my theoretical, and I'm actually put numbers in with them in just a second. What am I adding here? 4x's. Do you see how the coefficients are guiding you through how much you subtract and add? Yes? Okay, thank you. So if x is equal to 1, you subtracted 2x there, so you subtracted 2 molar there. How much are you subtracting here? 2 molar again, because it's the same quantity, because it's the same ratio of both of those reactants. So how much are you adding of C? 1 molar, because 1x is only 1 part, so you're adding 1.0 molar. And that's true because it's a 2 to 1 ratio. Keep going. 4 molar, because you have a 2 to 4 ratio, so a 2 to 4 ratio of the additions and subtractions here. So those are happening during the reaction. At the end, at equilibrium, you have 4 minus 2, so 2 molar, 4 minus 2, 2 molar, 0 plus 1, 1 molar, and 0 plus 4, 4 molar. These are the only important numbers at this point in time. The ones at equilibrium. These values here. Because this is what you plug into K. Because tell me what is K called again? Equilibrium constant. It's not called the initial constant. It's not called the change constant. It's called the equilibrium constant. So you have to have values from equilibrium to plug in there. So you see why you have to make the icebox to get down there? Okay, so plug those in and tell me what you get. What's C? 1, okay. What's A? 2 squared, right? And what's B? 2 squared. So you get 1 over 16, which is 6.25%. There you go. The K is 0.0625. Reactants or products favored? Reactants, because it's less than 1. All right, so I want you guys to start 4. And I can do it with you, because this is a much more complex example than what I've been doing. But I want you to start and then ask me questions. I'll leave this sample up here so you can use it. Thumbs up if you got this so far. Okay, keep going. Just making sure you're assuming 0 for products. Anybody got an answer yet? What you got? I think that's right. I don't have my key in front of me. Did anybody else get 27? Okay, tell me the first step you guys did after you got this far and you kind of set up your givens. You got your 2.8 molar here. What was the very first thing you have to figure out? What's x? Great. So x is just our kind of theoretical number behind the scenes that's helping us to find what each of these things you're subtracting or adding to. So how did you figure out what x was? Okay, C has a coefficient of 1 and?
And 2.0 equilibrium is 2.0, so you know that whenever x goes 0, multiply the coefficient by that to get 2.0.
Okay, so there's only 1x here, right? So C, you're adding 1x to get from initial to an equilibrium. You're adding 1x here. Well, what's x? 2.0. So to the side, you should write out x is equal to 2.0, and don't forget it, because once you figure it out, just use it the rest of the time. How many x's are you subtracting here? 1x. You're subtracting 1x there. So if x is equal to 2, what's equilibrium here? 1.0. How many x's are you subtracting from B? 2, because the coefficient is 2. So 2 times 2. 2 times 2 is, I just put 6. That's probably because I was trying to do it blind. Did I put 6 or 4? I can't read my, scratch that. That's 4. That's a 4. And that's a 4. And so is that down there. I tried. Okay, so you find that you've subtracted 1x there, so 3 minus 2 is 1. You subtract 2x's here, so 8 minus 4 is 4. You added that one, we already had that one. And then D, you have 3 as a coefficient, so 3 x's, and 3 times 2 is 6. So that's why in the end you get 6. Thumbs up if you understand how to do the icebox. Some of us are still working on it. Okay. So once you do get your icebox done, it's easy. You have your equilibrium values, and you plug them into your equilibrium expression. Don't forget, you do have to cube stuff and square stuff. So 6 cubed is, what's 36 times 6? What is it? 216 over 4 squared is 16. So 216 over 16 was 27. Answer? Yeah? There you go. All right. The other one I want you to do is number 5. We just did 4, right? Yeah. You guys write down, one second. Write down, you're doing number 5 on that same sheet of paper you've been working on for the past 10 minutes. And then on your problem set, which is on your paper, circle these for me. You have your problem set in front of you. Problem set 18. I printed it for you. Circle for homework tonight. 1, 2, 5, 6, and 7. So you have 6 problems to do right now and or for homework. So PS is 1, 2, 5, 6, and 7 plus that number 5 that I'm not going to do for you right now. I want you guys to try it. 5 from big sheet. Okay, and I'll come around for questions. I also need to pass out some things. The last thing I just want to tell you about, in case you have extra time tonight, is I had an oopsie moment on a test or another thing, and I need to replace that grade assignment. Got it? You do not have to do this. This is optional. But if you would like to replace a grade, I do something called the ABCs of Chemistry book. It's super fun and creative. ABC book is only, it's an easy assignment to do next Thursday. You choose every letter of the alphabet, you choose 3 words. So for letter A, you choose 3 words of chemistry. So this is a biology one, but acid, abiotic factor, and algae. Quick definitions, it doesn't have to be long textbook definitions, it can be in your own words. Those 3 words must be unique, okay? You just choose ones that we've talked about though, nothing that you've never heard of in your life. And then for every letter of the alphabet, you choose one to indicate, to depict, and your picture, your illustration must have a caption with it that is informative. So this one says, "Hey, I'm Margie and I'm a plant-like protist." Okay, it doesn't have to be that, but it can be something related to the word that you are drawing. These do not have to be drawn. These can be printed. That is okay. But if you want to do it electronically or, make a book like on a PowerPoint or a Word file, you need to print it and give it to me because I'm going to grade these and pass them back for you because they're really good for studying. Every single letter of the alphabet should have 3 words starting with their given letter, but you might have a hard time. No, I think we should be good with Q's. Maybe not U's. So if you can't find something with it at the beginning, find something with it with the letter in the word someplace. Z's, stuff like that.
Replace it like a password grade or
Any grade that you want me to, not Mythbusters. That's it.
so even
A bad test grade that you got an AP test last week, and yeah. You're welcome. Make sure you have it done by next Thursday. Yeah. For every in a caption for picture. And this was beautiful, but they turned it in 2 days late, so they got an 80. But hey, that's probably better than a 40. Yeah. Yeah, I just considered.
Wait, so we're going to test grade
Everybody has something to do.